So in this screencast on alcohols and ethers, we're going to look at the chemistry of epoxides and how we can make them from alkenes. So let's go ahead and start with looking at what is a peroxide. So peroxides have an oxygen-oxygen bond, and so we'll look at two specific examples, the first being hydrogen peroxide, which you're probably familiar with. If you ever gotten a wound, you can pour hydrogen peroxide on it. It's usually sold commercially as about 3% in water. So this is HOOH, hydrogen peroxide. Another common organic peroxide is meta, then the underline just means italicized, metachloro peroxybenzoic acid. This is abbreviated Mcpba, and it has the structure of the following. And so what does the meta mean? Meta is a relationship that's used for di-substituted benzene rings, which we have shown. So meta is specifically a 1-3 relationship, so we could also call this 3-chloroperoxybenzoic acid. So you see that peroxide bond here, you see it there. In general, that's what's indicative of a peroxide. So hydrogen peroxide is the simplest one. As you can see, there's those sort of three common elements, and then what we've done with this other hydrogen here is put an organic group on it. And again, that makes it soluble in organic solvents. It also gives it different electronic properties to affect the chemical reactivity. So peroxide bonds are usually pretty weak. So this is 213 kilojoules per mole. So it's pretty easily cleaved. And the hydrogen has a pKa that's definitely lower than your standard alcohol. So pKa of 12. So recall that's about 4 units less than a standard alcohol, so that's an acidic proton. So let's look at some reactivity of these reagents. So we'll look at reactions with alkenes to form epoxides. So let's look at our first example here. We'll take hydrogen peroxide. In the presence of sodium hydroxide in water. And so what this is going to generate, it's going to do an acid-base reaction. So this is a base, this is an acid. It's going to do a deprotonation, so we'll generate sodium, and then this peroxide anion. And then in the process, we're losing water as well. So this species here is a nucleophilic source of oxygen. So we have the oxygen nucleophile, then we have this weak bond still, and then we're going to look at this as a leaving group. And I know I've said that hydroxide is a poor leaving group, but this is a special circumstance where based on the weakness of that bond, it's actually a decent leaving group. So we're going to take that and we're going to treat it with the following compound. So which is an alkene. So we have this alkene. This is a tri-substituted alkene, so 1, 2, 3 substituents. Next to this alkene is this carbonyl group, and that actually imparts some important reactivity on the alkene itself, and that's demonstrated through the use of resonance structures. So we can draw a resonance form, which I'll draw that using this red arrow to show how we can move these electrons to predict the reactivity. So this resonance form helps us understand how this nucleophile reacts with this compound, which is an electrophile, specifically at this position. So we're able to do this resonance form because the oxygen, which is electronegative, can accept this extra lone pair. We now have an electron deficient carbon, and so what ends up happening is a lone pair will attack that carbon. We then can push arrows just as we've shown with the resonance form. Let's draw the intermediate that's formed here. So again, this anion, this oxygen nucleophile is attacking this position. These electrons then flow up onto oxygen. So now within this molecule, we actually have a nucleophile. So let's a nucleophile and an electrophile. Let's draw a resonance form of this. Which we reestablish the carbonyl, and then we're putting the electrons on that carbon. So that carbon's negatively charged. We're balancing out with the sodium. And so now what happens is this carbon will attack that oxygen, and then we will break that weak bond, and then hydroxide will leave. And so when we do that, so the bond we just formed is that one. So we can see that that's a 3-membered ring. In the process, we're generating sodium hydroxide as well, which is fine because we actually have it in the starting medium up here. So we see we have 1, 2, 3-membered ring. This is an epoxide. That's the functional group. And so this reaction will only work when you have an alkene with a directly bonded carbonyl group to it. So in the second reaction, we're going to look at the action of Mcpba on an alkene. And this can be any alkene. It doesn't have to be one that has a carbonyl group on it. So let's take this compound, which ends up being 1, 2, 3, 4, 5, 6. So this is 1 hexene. It's a monosubstituted alkene. You can see there's no groups bonded to these positions that can present a scenario as we saw above here. So this is your standard run-of-the-mill alkene. And what I'm going to do with say the green pen here is I'm just going to highlight this oxygen. I'm just going to fill it in because that's the oxygen that's actually transferred to the alkene under these reaction conditions. So we would use a solvent like chloroform, a polar aprotic solvent, to initiate this reaction. And so what's happening is a couple things in terms of how that oxygen gets transferred to that alkene. To form the epoxide. So we have a nucleophilic oxygen here. It's going to attack the carbon. We have to break the carbon-carbon pi bond. And so the oxygen is going to add across those two carbons. So the pi bond is going to come back around and attack that oxygen. So that may be a new sort of mode of reactivity that we haven't seen before, where we have an oxygen acting as a nucleophile, attacking an electrophile, then the electrophile itself acting as a nucleophile, attacking that electrophile. So that's really what we mean here when we're showing that. So we have to break then this bond and this bond. And so how this is going to happen, we can envision as this arrow comes here, we can break that bond. So the way we'll show that is going to form this double bond. This double bond will then cleave to come up to abstract that hydrogen. And then we break this bond, and it's going to restore electrons back on that oxygen. So that's quite a bit to take in. But essentially what it's going to do is leave everything in its sort of normal valency. So overall, we're installing that oxygen at that position. We have our rest of the chain, which is left unadulterated. And then the other byproduct here is this metachlorobenzoic acid now. So you can see by what's left over that this oxygen is transferred to the alkene to generate the epoxide, and then the remainder of that functional group now becomes just a benzoic acid derivative. So in this next slide here, we're going to look at the epoxide reactivity in both acidic and basic media. So what I'm going to draw is just a very generic epoxide to begin with, reacting with an acid, and showing what are the possible routes that can happen under that reaction media. So here's our epoxide. And I'm going to use just very general R1, R2 groups. So whenever we're given an epoxide, the first thing that we want to do is look at the two carbons, so the sp3 hybridized carbons that are bonded to that oxygen. And then we want to classify them as if they were separate alcohols. So the one on the right here, we would classify this as a primary alcohol, and the one on the left, if both R1 and R2 are carbon, we would say that is a tertiary alcohol. And so that is important when we are in either acidic or basic media, because it helps us determine which carbon is actually going to undergo the reaction. So say we're in the presence of an acid, which I'm going to call HA. So HA is the acidic medium. So the first thing that's going to happen is an acid-base reaction. So if this is our acid, the epoxide then is our base, and specifically the electron pairs of the epoxide oxygen will do the proton abstraction. And so with a curved arrow, we can show the oxygen being protonated. We then cleave the HA bond, and we end up with this protonated intermediate. So again, for those of you who did not have me last semester, R1 and R2 are basically, they can be any other functional group, and we're just being very general here. The hydrogens are what they are, and so when we get to this stage, we see that we now have developed a plus charge on the oxygen that's balanced out by the negative charge on the conjugate base of our acid. So since we're in acidic medium, now what we have to make a decision point on is the following. So I'm going to say we're moving forward, and then we can go either one way or we can go another way. And what those ways are, so if I show, I want to call this bond A and this bond B. I'm going to call this route A, route B. And so if we're going along, if we're taking route A, essentially that means if we open up this bond, so we're going to ionize that bond. And because R1, R2, and this carbon are all carbons, that would mean that we form a tertiary carbocation here. And so as we go along, boom, that's what we're going to draw there. And so the reason this happens is because we have a three-membered ring in an epoxide, and so that wants to open up to relieve that strain. And so when that opens up, we're essentially now rehybridizing to sp2 hybridized carbon. So let me just draw in the p orbital. There's the plus charge, OH. So this would be classified, again, matching what we started with, a tertiary carbocation. Now if we went to route B, and that bond ionized, this would be going up this path. And the reason I have it going up is because it's going to be higher in energy, and it's not going to be the preferred route. But we need to draw it anyway so that we can properly evaluate it. So if that opens up, we now end up with a primary carbocation. And again, when we recall carbocation stability, we see that's the trend. And so the reason that it's important to draw this, what I'm going to call a bifurcation point, is that it allows you to draw both intermediates. You see the structures, you then can compare them according to the trend, and you know that, okay, this is the more stable one, slower in energy. This is the one that's going to proceed in the reaction. So that's what you have to do when you're looking at epoxide chemistry, is make a choice where the reaction is going to proceed. So before we actually get into a specific reaction, let's look at epoxide reactivity. In basic media. And then what we'll do, for an example, we'll take one epoxide, we'll treat it under two different sets of conditions and see how the acidic or basic nature affects the reactivity. So if we're looking at that other epoxide we started with from above, now I'm going to draw it in the middle. So I'm going to draw two routes going this way. And as we saw before when we evaluated those carbons of the epoxide, we said this would be viewed as a primary alcohol, this would be viewed as a tertiary alcohol. So if we're treating under basic conditions, say we have a nucleophile, this So I'm going to say Nu lone pair minus some nucleophile. So now this is under the SN2 regime, whereas above you could think about it more as SN1. So now since we're under SN2, we know that primary is greater than secondary is greater than tertiary. And so that's how we're going to make our choice here in which way to go. So the nucleophile is going to attack the primary carbon and not the tertiary. So let's just write primary here, tertiary there. And so if the lone pair attacks, again, it's opposite the CO bond, because that's then going to open. So remember the stereochemical outcome of an SN2 reaction. So this is how it would proceed, but let's just go ahead and draw the product if the nucleophile were to attack this carbon. We'll just draw that over there so we can visually see. So I always encourage students when they're learning this to always draw out these different possibilities so you can make the best decision possible. So essentially, when you look at both of these, the route that is preferred again is the primary. The nucleophile, carbon-carbon bond oxygen. See how it's anti? You also see that as here, nucleophile, carbon-carbon oxygen. It's anti. The tertiary route is obviously not preferred because we're under SN2 mechanism. But it's always nice to see what your possibilities are and then argue your way through why one is preferred and one is not. So if we're looking at a specific epoxide, so say we consider this epoxide here, and we then are going to treat with different sets of conditions. So here maybe we have HCl in methanol as the solvent. So we're under acidic media there. Then on this side we're going to treat with potassium cyanide and DMSO. So a big part of organic 2 is obviously when you're given a starting material or a reactant, identify the major functional group. So it's an epoxide, there's 1 degree of unsaturation. Diagnose the reaction conditions. That's something you need to be good at doing. We have an acid, HCl, in methanol, polar protic solvent. So acidic medium. So if we do our analysis, we can see that this carbon here is primary. That carbon there is tertiary if we're classifying according to alcohols. So under the acidic conditions, we're going to cleave this bond because it creates a tertiary carbocation. That then allows the solvent to attack that position. Then after a proton transfer, we're going to end up with the following. So I'm just going to draw in, you can see that anti-relationship there, and then I'm just going to draw in the other substituents. So that shows you how the epoxide opens to give the tertiary carbocation, which is then trapped by the solvent, and then after a proton transfer, we end up with a neutral ether. So under these other conditions, which are basic, because we have potassium cyanide, dimethyl sulfoxide, so this is SN2-like, we're going to attack here. which means that this bond is going to be retained at the tertiary carbon. So this bond is retained, OH. There's the carbon-carbon bond, and we're adding cyanide, so CN. So that would be the product, again, from that different set of conditions. So SN2, SN1. So most of the reactions that you learn in Organic 2 will have some flavor of the mechanisms you've already seen from Organic 1. So in one last slide on alkene to epoxide chemistry, we're going to learn another reaction of epoxides. So we'll call this we'll say alkene to epoxide to anti-diol. And so if we consider the following substrate, and I'm going to put some perspective on this. So this is going to be cyclopentene. So there's the alkene of cyclopentene, then here's the ring. So we're sort of looking at the edge. And we're going to take that molecule in step 1, we're going to treat with Mcpba, dichloromethane. And then in step 2, we're going to treat with water, a catalytic amount of sulfuric acid. And so let's draw the product of step 1, and then we'll look at how that is then reacted with the water and acidic medium. So if we take an alkene and we epoxidize it, let's just put, that's the epoxide, and we can put the substituents in. And then we have just a little bit of artistic flair here. So we're looking at the edge on, and essentially at this point, since we are starting with something that's achiral, this is achiral, it doesn't matter which face of the alkene we epoxidize, we do top or bottom, you end up getting the same molecule because there's an element of symmetry. However, in the next step, now that we've formed the epoxide and we're treating under acidic media, so we'll say H3O plus. We'll draw the intermediate that's protonated. So now at this point, if you look, since the molecule is symmetric, these two carbons are essentially both secondary. And so secondary, they're both equally going to be attacked by water, which is the nucleophile. So we can go attack here, alternatively attack there. So if we go ahead and draw those both, we can figure out what the relationship between them is. So if we say, if we look here, water is attacking this carbon, carbon bond, and then this we're cleaving this. So attack here, we cleave that. So we're going to have OH, carbon bond, OH. So let's just draw that first. So we put in the substituents that still exist. They're still there. This would be the compound from that attack. If this water attacks here and we cleave that bond, let's go ahead and draw that. So you can see at this point, these are mirror images of one another, and we'll go ahead and do a proton transfer to remove the hydrogen, and that's simply just with the water. So H2O. So PT, that's proton transfer. And again, this is happening equally because there's nothing to discriminate amongst the different faces from attack. So we end up with a pair of enantiomers. And again, these are diols. So this would be a racemic mixture. And if we were to take this mixture and put it in a polarimeter, the specific rotation would be 0, because whatever direction this rotates the plane polarized light, this rotates at the opposite direction. So they essentially cancel each other out. So this overall, as we see, this is where we're getting at with organic chemistry 2 here. We take one functional group, we transform it into another, and then a third. And obviously, if you think about all chemistry you know about alcohols, you could continue on. And so again, just to hammer this home, this is what synthetic organic chemists do, is take simple starting materials and then through a series of sequences of reactions, make things that are more complex. And usually you're looking to make some sort of property in the molecule that we can use, say a coating that makes a metal rust proof or makes a pan non-stick. So that's the importance of knowing these functional groups and what their properties are.